When we talk about molecules of a compound, we use empirical formulas and molecular formulas. For example, here we have acetic acid. The grey spheres represent carbon, the red spheres represent oxygen, and the blue spheres represent hydrogen. These are shown bonded together, represented by the grey lines. The empirical formula for acetic acid is CH2O. The molecular formula is C2H4O2. The empirical formula is the simplest formula with the smallest set of whole numbers of atoms. This essentially represents the ratio of the individual atoms that make up the compound. We can observe this by measuring mass percent. The molecular formula of a compound is the formula of that compound as it exists, with the specific numbers of each atom that exist in the compound, and is always a multiple of the empirical formula. If the molecular formula of a compound is known, or the empirical formula, we can use this to determine the mass percent of each of the different elements in the compound. Here we have glucose, which has a molecular formula of C6H12O6 and has a molar mass of 180.16 grams per mole. There are 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen in 1 mole of the glucose molecule. We can see here the mass of each of those components, and we can also determine the mass percent. Mass percent can be found using empirical or molecular formulas. We can also measure the mass percent using combustion analysis. Let's work through the calculation of the mass percent of carbon in a glucose molecule. There are 6 moles of carbon atoms per mole of glucose molecules. We can use the molar mass of the carbon atom to get this in terms of grams. The moles cancel, and we see that there are 72.0 grams of carbon in 1 mole of glucose. We can then divide this mass of carbon by the overall mass of the molecule and express it as a percentage. The grams cancel, and we see that there is 40% by mass of carbon in the glucose molecule. We can do the same calculation for the hydrogen and the oxygen and determine the mass percent of each of the atoms in the glucose molecule. The reverse calculation can be done to determine the empirical formula for mass percentages. For example, if we use combustion analysis to determine the mass percentages of each of the carbon, hydrogen, and oxygen, and we know the molar mass, we can use this to determine first the empirical formula and then the molecular formula. Mass percent tells us the empirical formula. By combustion analysis, we can measure the mass percent of each atom in a compound and use this to determine the empirical formula. Sample 3.5 in the book goes through this. If you want to determine the molecular formula from the empirical formula, we also need the molar mass. So, together with mass percent, molar mass allows us to determine the molecular formula. Sample 3.6 in the book goes through this. It is important to note that mass percent does not provide structural formula. What this means is we don't know how the atoms are connected together. We just know how many of each atom is in the molecule. It's possible to have the same molecular formula but a different structure. Molecules with the same molecular formula but different structure are called isomers. On the left here we see a molecule in which the 4 carbon atoms are arranged in a single line. These are the black spheres. On the right we see a molecule in which the 4 carbon atoms are not arranged in a line. Here they are in a propeller type shape. Those 4 black spheres are arranged differently. The molecular formula for each of these structures is C4H10, but the structure of the molecule is different. Isomeric structures can't be determined using mass percent, not even if we have the molar mass.